Welcome to The Explainer. Today, we're diving into what is arguably the ultimate paradox of modern technology. We are literally standing right on the edge of a breakthrough that promises both total digital destruction and, at the exact same time, the greatest scientific renaissance in human history. We're talking about quantum computing, the looming collapse of modern encryption, and the ticking clock toward what experts are calling Q-Day.
Okay, let's dive right into this, because this is the massive stakes-raising question we really have to answer. What actually happens when the math protecting the entire world suddenly just breaks? Seriously, think about your bank accounts, your private messages, or even just that little secure HTTPS padlock on your web browser right now. We all walk around feeling pretty secure, right? We assume our digital lives are locked up tight in this impenetrable vault. But here's the catch. That vault isn't made of steel. It's made of math. And that math is fundamentally tied to the limits of the computers we use today.
And there's a quote that just perfectly captures the gravity of this. The entire planet is dependent on a digital system whose foundations are about to collapse. Just let that sink in for a second. Every secret you've ever kept online, every single financial transaction, every confidential government communication, it all relies entirely on an assumption that is rapidly nearing its breaking point.
Section 1. Binary versus quantum superposition. So, to really understand this, we need to look at the core difference between the computers we've been using for the last 70 years and the machines of tomorrow. From the smartphone in your pocket to the computers guiding spacecraft, everything today runs on binary, good old ones and zeros. But quantum computers, they use qubits. And thanks to the frankly bizarre laws of quantum physics, a qubit doesn't actually have to choose between being a 1 or a 0. It can exist in a superposition of both at the exact same time. And I really want to emphasize this point. This isn't some clever metaphor. It's not just a fancy analogy for being fast. This is literal, observable physics that allows for multidimensional parallel processing. Think of it like solving a giant maze. A classical computer has to check every single path, one by one. Hits a dead end, it has to back up and move to the next. And honestly, no matter how incredibly fast we make our classical computers, they're still just flipping binary switches, checking those paths in sequence. But a quantum computer, it explores the entire maze all at once. It literally leverages the fundamental rules of reality to process information in parallel. It's an absolute game changer.
Section 2. Cracking the uncrackable math.
Now, what's really interesting about this is how this mind-bending quantum power actually targets and neutralizes our modern security. Let's do a quick thought experiment. Imagine you're running the world's biggest intelligence agency. You've got an unlimited budget, unlimited supercomputers, and your mission is to crack just one message secured by standard RSA encryption. Here's the deal. If I ask you to multiply two prime numbers together, say 107 and 109, you easily get 11,663. Easy, right? But if I give you 11,663 and ask you to find the two original prime factors, that is significantly harder. Modern encryption scales this basic idea up to numbers that are hundreds of digits long. For a classical computer to find those primes, it would take something like 1 trillion years. It acts as an unpickable lock because it literally forces a step-by-step machine to guess more combinations than there are atoms in the observable universe. No way around it.
But, as we established, a quantum computer doesn't guess step by step. Using a mathematical master key called Shor's algorithm, it explores the factors simultaneously. And if you're sitting there thinking, oh, we're decades away from this actually happening, well, look at Google's recent 105-qubit Willow chip. They ran a complex benchmark test on it. To give you some perspective, for a classical supercomputer to complete this exact same test, it would take an estimated 10 septillion years. Guys, that is 720 quadrillion times longer than the age of the universe. But the Willow chip, it did the whole shebang in 5 minutes. 5 minutes. So this obviously sets a pretty terrifying ticking clock. Back in 1994, Peter Shor proposed the algorithm to break encryption. Then in 2024, Google's Willow chip proved that quantum error reduction at scale is actually possible. And by 2035, experts estimate we'll cross the horizon and hit Q-Day. The wall standing between us and totally broken global encryption is no longer a matter of physics or math. The math is beatable, the physics is achievable. It's now simply an engineering problem.
Section 3. Harvest now, decrypt later.
Let's pivot to the present day for a second, because this isn't just a future problem, it's an immediate crisis. You might be thinking, well, my data's encrypted right now, so I'm totally safe until 2035, right? Well, not exactly. Bad actors, intelligence agencies, hackers, they're already operating on a terrifying principle.
Harvest now, decrypt later. They're out there quietly vacuuming up dormant crypto wallets, cloud storage, private emails, and corporate secrets. Sure, they can't read it today, but they're treating it like Schrodinger's data. They're just stockpiling it in the dark, waiting patiently for the day they finally get their hands on a master quantum key to unlock it all. To really put the terrifying scale of this data harvesting into perspective, consider the Stasi in East Germany. They maintained one of the most invasive surveillance states in human history, generating 111 kilometers of paper files over 40 years, which, by the way, is a lot of paper cuts. But today, major intelligence agencies generate more surveillance data than that in a single day. The only thing standing between that harvested data and total exposure is encryption. On Q-Day, encryption completely stops being a safeguard. It simply becomes a temporary delay in the timeline of your exposure.
Section 4. The fragmented post-quantum internet.
So what does our internet actually look like when those cryptographic foundations begin to shatter? And this brilliantly illustrates exactly what's at stake. Let's look at a real-world digital handshake today. You buy something online. Your laptop in Sao Paulo seamlessly handshakes with an Amazon server, which then talks to MasterCard, which talks to your local bank, which talks to a global settlement system. Boom. Dozens of digital handshakes across borders in a matter of milliseconds, and they all trust each other flawlessly because they speak the exact same cryptographic language. But in a post-quantum world, that uniform trust is totally broken. Migrating to quantum-proof standards is currently being called the largest infrastructure project in the history of the internet. Naturally, wealthy nations and major banks are going to migrate first, but smaller institutions and developing economies, they're going to lag behind. And when two systems try to connect, the security is only as strong as the absolute weakest link. The internet won't die per se, but the single open internet we've trusted for 30 years is going to split. It'll fragment into a tiered system of heavily guarded safe walls and highly dangerous digital wastelands. Section 5. Unlocking the post-digital age. Okay, now I want to pivot entirely. Because if we only focus on the doom and gloom of broken encryption, we completely miss the breathtaking, wonder-filled promise of this technology. So the crucial point here is that classical computers are hitting a hard physical wall. For decades, we've relied on Moore's law, the consistent doubling of computing power. But transistors are now literally just a few atoms wide, and at that microscopic scale, electrons start tunneling and behaving completely unpredictably. We have hit the absolute limits of physics for binary systems. Classical machines just cannot simulate complex molecular interactions or advanced chemical reactions because the variables simply explode into infinity. Just look at medicine, for example. Today, drug discovery is honestly a bit like throwing darts blindfolded. It's incredibly slow, super expensive, and relies heavily on trial and error approximations. Why? Well, because molecules are governed by quantum mechanics. Classical computers just have to guess at how they work. But quantum computers? They will be able to precisely simulate the exact molecular and electron interactions. We won't be guessing anymore. We'll literally be engineering cures at the most fundamental level of reality. How wild is that? The quantum promise is absolutely staggering. Right now, we basically just optimize within the constraints of materials we accidentally stumble upon. But quantum computing lets us design from first principles. We could simulate room temperature nitrogen-fixing enzymes, which would completely revolutionize global fertilizer production without the massive energy waste we have today. We could design hyper-efficient battery chemistries that finally solve our global energy storage crisis, or calculate perfect, flawless optimizations for power grids around the world. But, and this is a very big but, we do have to ground this excitement just a bit. There is a massive quantum bottleneck. Unlike the smartphone in your pocket, there is absolutely no quantum laptop coming to consumers anytime soon. These machines are unbelievably expensive, incredibly fragile, and require cooling to temperatures that are actually colder than deep space. Which means unimaginable, world-altering computing power is initially going to be concentrated in the hands of a very small, select few global institutions. Which leaves us with perhaps the most important question of all. Who gets to build the civilization of the post-digital age? You know, the digital age, for all its flaws, really democratized access to technology. But the post-digital age is different. The geopolitical and societal consequences of who funds, who licenses, and who ultimately controls the quantum supply chain, that is going to define the next century of human existence. I want to leave you with this thought. Right now, you're standing in a doorway. The room behind you, the digital age of the last 70 years, is closing on its own. The room ahead of you is being built whether you step into it or not. You are existing in a literal state of superposition right now, simultaneously incredibly excited for a world of scientific miracles and deeply terrified by the collapse of our digital security. The future is being written in an entirely new language as we speak. So the question is, will you stay awake to see how it's built? Thank you so much for joining me for this explainer. Keep questioning, keep learning, and I'll see you in the next one.